So we're going to take a data set called data is about the number of international airline travels per month. So that's there for 12 years. So we've got 144 observations. So I'm going to show you the data. So I've already taken the data in my work library, but if you go to the SAS help, you will see that the data set there. Okay, so we've got variable of interest, which is the time series variable, is the variable called air. So air is the name of the variable and is also the name of the data set, by the way, so don't get confused. Okay, all right, first thing that we're going to do is to plot this data set. Okay, how does it look like? We have a scatter plot, and this is how it looks like. Okay, we've got international airline travels in the y-axis and jet in the x-axis, and this is how it looks like, right? You can form some opinion about it, whether it's a stationary data, whether it's non-stationary data, whether there is seasonality or there is no seasonality. Get all the descriptive statistics about this data. And how do you get it? We use the procedure proc called proc Arima, and we'll use this data set, data air, and the keyword that we're going to use is identify, and the time series variable is the variable called air, and then we'll use an option called n lag equal to 24. Well, n lag is equal to 24 is nothing but that we want to see how the data behaves for its 24th lag. Okay, so you can have 36 lag, 48 lags, and so on. So it's an option given to you. You can, usually you get it for 12, for 24, or 36, and so on. It's only for, there's no model building happening here. So you have that option of, or the luxury of changing things and getting different kinds of descriptive statistics from this data. So you don't have to worry about what exactly should be the n lag at this moment. So don't worry about that. And let's run this. So this is purely an exploratory data analysis at this moment. So we have this option of keep trying different n lags. Alright, so you get the mean, the standard deviation, the number of observations, the different lags, and the correlations, the autocorrelation rather. Why we call it autocorrelation? Because the correlation of the series with its own lag. That's why it's called autocorrelation. Right? Auto means self, correlations means self, correlation with itself. Alright. Okay, so you see there is correlation. Of course there is correlation because all these things are significant. As you see, the p-values are less than 0.05, so there is correlation, right? Autocorrelation, which is a good thing because we want our present value in the time series to be correlated or to be related to its past value, and that's the reason why we are going to use Arima model for forecasting. If that's not there, then there's no point building a time series model. It's purely random, and it's not going to help you forecast your future values correctly. Okay, so at this point in time, let me tell you that if you're not familiar with time series theory, please go back and watch my video on time series theory on my channel. There is a 1-hour video on time series theory. Please go ahead and watch that video. You can go to the playlist and watch the time series theory video on that playlist, and you'll be familiar with the basics of time series modeling. And then you can watch this video to see how you can build it using SAS. There are other trend and correlation plots. Yeah, we'll see these plots, the autocorrelation function, the partial autocorrelation function, the inverse autocorrelation functions, and so on. Okay, all right, so what do we get out of this autocorrelation function and partial autocorrelation function? Well, one thing that we are very sure of is that this data is not stationary. Even from the plot we could see that it doesn't seem to be a stationary series. For stationary series, the mean and the variance should ideally be constant. Okay, and it doesn't seem to be the case, right? Also, if you look at the PA to the autocorrelation function graph, the ACF, there should be a sudden drop of in a stationary series, but that's not the case here. You see the drop in the ACF value is, is not steep. It's rather quite flat, and that's not the nature of a stationary series. So it's clearly a non-stationary series. Okay, and PACF, we use it for identification of the number of number of the order of the Arima series, Arima model. Okay, and we'll discuss about that. IACF we never quite use. We very seldom we use, so we don't really look into IACF. Using SCF and PACF, you can very well build an ARIMA model without looking into the IACF. Okay, so the two things that we are uh, very interested to know is whether the series is stationary and whether it is a white noise. So white noise series is basically a random series. So you do not build a time series model on a white noise time series data. So if the data is white noise, you simply leave it there. You cannot build a time series model because it's purely random. There is no point building a model. Well, you can actually see whether there is the data is white noise by looking at the autocorrelation check for white noise. Okay, and you see that the p values are all significant. That means it's not purely random. There is highly uh, highly high correlation between the lags. Okay, and it's not purely random. Hence, series is not white noise and it is non-stationary. So these two things are clear at this moment. The next thing that we'll do is to convert this stationary time series to the non-stationary time series to a stationary time series. And how do we do that? We do differencing. So differencing is just about subtracting the lag from its value. So this first order differencing, the second order differencing, we start with first order differencing and we see then whether the time series is now stationary or not. Okay, if it is not stationary, then we go ahead with second order, and then if it is still not stationary, then we go ahead with third order stationary. But most of the times you will get a non-stationary series to be stationary in just first two differencing, so you don't have to go to for third differencing and so on. But yeah, but you still can try. If you are familiar with time series theory, you might be wondering why aren't we doing the statistical test for stationarity checks. Like you can do Dickey-Fuller test, augmented Dickey-Fuller test as well, ADF test as well, right? So you can try that as well. So I'm not going to use ADF for stationarity check, but you certainly can do that. Okay, but you also can look at the series and also look at the ACF value and get to know whether it's a stationary series or a non-stationary series. So we're going to do the first order differencing. How do we do that? So identify var and then the variable that is of interest to us, in bracket just put 1, and that's how we do the first order differencing. And when you do second order, simply change it to 2, and then it's going to be second order differencing. So let's first do the first order differencing, and we'll see whether we get the non-stationary series as stationary series in the first order itself. So what we're going to look at is the ACF. Well, now you see there is a steep decrease, or there is a sudden decrease in the ACF values, right? It's not flat anymore. So it seems that with a first order differencing, we get stationary series instead of a non-stationary one, right? So so we're fine with first order, but we also can look at the second order just to be sure whether the second order is better than the first order or not. Okay, but if both are stationary, then we'll go ahead with first order. Okay, because having less terms is always better, right? Well, you see, this is not better than the first order, so we'll go ahead with the first order, right? All right, so that's done. The next step is the estimation and the diagnostic checks. Okay, so there are three steps in time series model building. First one is identification, the second one is the estimation and diagnostic check, and the third one is the forecasting, right? So these are the three steps in a box thinking method of time series forecasting, right? So the syntax for estimation is very simple. Is use just estimate and then provide what model you're going to estimate, right? So that's something that you need to put in, right? So whether we go to AR1 or MA1, ARMA1, Arima 111 and so on, right? Sorry, one ARMA 11. So how do we know which model is to be used? Okay, so let's look at the plots again. Okay, so let's use the first order differencing, and then okay, now the thing is there is a strong correlation between the lags. So one thing that we are very clear, right? That means its own lag. That means if yt is the time series, it has high correlation with yt minus 1. So clearly there is a AR term, right? Whether we're going to have a MA term is not, whether that's going to make the model better, we'll see later. So we can try several models to see whether we can use MA term as well in combination with AR terms. Okay, but now we have already done the differencing. Okay, so there is already the I term. In Arima we have AR and I and then MA, right? If you're familiar with the time series theory, there are three terms: P, Q, R. So P stands for the AR term, Q is for the differencing. So we already have first order differencing, Q equal to 1, we already have it. And then we have R, which is the MA terms, right? So so here the MA term, we'll see whether we actually need the MA term. We'll start with the AR1 and then we'll see if adding the residual makes any difference. So for MA we are using P equal to 1, and if you're going to use the MA, okay, I'm sorry, for AR P equal to 1, for AR1, for AR2 if P equal to 2, and so on. So for AR term it's the P, and for MA terms it's the Q. So here you see we're going to use both P and Q. So here, so we will estimate the AR1 model first. Okay, now remember that we have already done the differencing, so the I term is already 1. In the Arima, the I term is the differencing, right? It stands for the differencing. We've already done the first order differencing, right? So it's already 1. So we'll keep that in mind. Okay, so so for AR1 we use the P equal to 1, okay, in the estimate along with the estimate keyword. Okay, all right, so we will run that. Okay, remember this is for the differencing series, differenced series, so it's basically Arima 110, okay, not 100. So that's something we need to keep in mind. All right, you see the terms here. We have mu, so these are the estimates. We have mu, which is the average, and then you have the beta coefficient, which is the 0.305. it's also significant, right? It's less than 0.05, so it's significant. So that's the AR1, and you have all the diagnostic statistics like AIC, SBC, and so on. So these are going to be used while comparing the time series models, right? So the one with the least AIC and SBC should be the one to be to be selected finally, right? And then we will see the autocorrelation of residuals. Okay, so the idea is to see to ensure that the residuals are not autocorrelated. There is no correlation, but clearly there is some correlation, right? The p-value is significant, so the residuals are correlated, indeed correlated. Let's look at the normal residual plot, and you see that it's not normal, right? So there are two things, signal that tells us that this model doesn't fit the data quite well. Firstly, the residuals are correlated, and the plot doesn't seem to be a normal plot, okay, or it doesn't seem to be a normal distribution. The residual doesn't fit a normal distribution. Hence, we will see other models, right? We'll add the MA terms, which is the error term, to the model, and see if it makes a model better or the forecast better. Okay, so for MA we use the keyword Q equal to 1. So we'll start with MA1. Okay, okay, let's run this one. Of course, you can use P equal to 2, Q equal to 2, P equal to 1, Q equal to 2, P equal to 2, Q equal to 1, and so on. So we can try all sorts of combination and see which one is the best model for this data. Okay, we'll see the autocorrelation. There's still some autocorrelation between the residuals, so the same problem exists, but the residual plot is much better, right? It's more normal now. So this model is better than the previous one. The Arima 111 is better than Arima 110, right? So this is clear. Okay, we can try with other models. Okay, there's no issue with that. So we can try, let's say, P equal to 2 and Q equal to 1, and let's see if that's better. It's not better, in fact it's worse. Okay, so this one is the best one, right? The Arima 111. Now you might wonder why we have 3 ones. Well, we have P equal to 1, which is the AR term, then this is the differencing term, the first order differencing, and this is the MA term. So we have Arima 111 is the final model for us, right? Because among the 3 models that we've seen, the Arima 111 gives better results. Like looking at the diagnostics statistics, we could know that this is better. You also can compare the AIC and BIC, okay, and see the one that's with the least AIC BIC should be the one we should choose. Okay, so that's about estimating, right? And the final thing is forecasting. Now that we are sure that we're going to go with Arima 111, we'll use that for forecasting the next 12 months values, right? Syntax is very simple. We'll use the same code, proc Arima. We'll simply add the last part to it, which is forecast, the keyword forecast, and then if we want for next 12 months, the lead is 12. If we want it for next 24 months, we want, we just use 24, or 18 months 18, and so on. Interval should be a month because it's a monthly forecast. ID, which is the unique ID, which is date, and we will save it in a new dataset called results. Okay, you can give any name. Okay, no problem with that. And then we'll use the same estimate. Okay, P1 and Q1. Okay, and this is the differencing. Okay, so don't forget this differencing part. Identify var equal to AR. So because the I the order for I comes from there. Okay, so it's a Arima 111 model, and let's use this to forecast the future values. Okay, we'll run this, and what we're going to get is the values, the forecast values, predicted values for next 12 months using Arima 111. Okay, and you can see the values. So these are the values. So we had 144 observation, now we have 156. That means we've got 12 additional observations, which basically are the future values. Okay, so these are the values, and you see the plot here, and also the 95% confidence limits. So this is how the forecast looks like, and then we have the 95% confidence limit. That means in which range the forecast will lie. Okay, so that's the way you build an ARIMA model using SAS. Thank you.